Hello and welcome back to Differential Equation, section 4.1 on first order systems. So we will be talking now about systems of differential equations. Today we are mainly talking about the setup and maybe solve some very basic ideas, right? And then we're going to improve on those solutions later through chapters 4 and 5 and so on, because there will be more talk about the systems. So far, we dealt with a single differential equation of first, second, third, whatever order, and we know how to solve those using the methods that we outlined in chapters 1, 2, and 3. Now we're focusing on multiple equations that are coupled, meaning that the same variables show in both equations. And we are going to learn first, how to set up these systems, what they mean, and then we're also going to take a look at some of the solutions to the system. So let's start with the idea of mechanical. Maybe it's the best usually. So we have one spring attached to mass 1, and then there is another spring attached to mass 2, and then you know that you can pull this with some force F of t. Now these springs can be different springs. One can be stiffer than the other, which means it's harder to pull or compress it, needs more force. And clearly that as you pull on the M2 object, the M1 object will also start to move, and when you let go, they're going to oscillate at different frequencies because K's are different. Now, each one of these masses has its own system. So remember, the displacement of the first object will be displacement x, right, which is a function of time to the left and to the right. And the displacement of the second object is also, but now this one will be y, right? Well, I mean, you can use x1 and x2 if you want, because they're both moving on the x-axis, and usually that is the better way, because generally we like to take a look at the up-down motion for y. Actually, you know what? Maybe it's better if we use x1 and x2, because we're using m1 and m2. Yeah, whatever. All right, so let's do this now. So now, what do I have? I have a mass, easy tablet. I have mass 1. This is what you would call in physics a free body diagram. And this one is acted upon with two forces. There is a force, right? Force using the Hooke's law with the kx or ky, right? Because both of these are displacements. So we have a k1x force to the left, because the only force applied on the left is the k1 force with the times x, sorry. So force that is due to the spring. And that one will be pulling or pushing depending on where the object is. Now, on the right-hand side, what you have is the K2 times the difference in displacement of y and x. And that should be, dare I say, common sense, because the force of K2 is, again, K2 times the displacement, and the displacement is the difference between the movement of M1 and M2. So there is the displacement here remember, when the object M1 goes to the left, it's trying to pull M2 to the left. The spring is actually stretching and trying to expand. Sorry, the spring is stretching and trying to compress, which turns into the opposite motion because the spring wants to go the other way. The spring always opposes its motion. So if you compress the spring, it wants to expand. If you expand, the spring wants to contract, compress. So it will always be the difference y minus x when you have the two objects in between, because they always want to go the opposite way, right? Remember, you stretch the spring, spring wants to compress, you compress the spring, spring wants to stretch. So these objects will always be in opposition because they are connected with a spring. If you connect this with a solid rod, then they move at the same direction, at the same, right? Then technically become one object, and you don't even need to, right? If you connect those with a rod, because the rod does not compress or stretch. But because you have a spring, whatever motion you exert on a spring, whether it's stretching or compressing, the spring wants to do the opposite, right? So the first body diagram has the two forces, right? Something is attached to the left, something is attached to the right. We're not considering the friction here. You could add friction, right? When you have the normal force, if the M1 is resting on some kind of floor, and then you would have also friction force, but we're not considering that now. Now the second body diagram, which is the M2, will have the spring coming in. So K2y minus x, we already have that. That's the same force because they're connected. And on the other side, you have the F of t, which is the pull, right, that we exerted on it, right? So to set the whole thing in motion. So there you have it. You can now write your equations, right, for motion using the second derivative. If you remember what we did before, so your mass 1 and then x displacement, right, in the x double prime is going to be equal to, now, negative. If you want to have this side to be the positive, then the one that pulls to the other way is a negative. So negative k1x plus k2y minus x. Right? So this one is pulling this way. If you take a look at the vectors, the way I draw them. And then this one is pulling that way, which is why it's negative. To model M2, you do exactly the same thing. Now this is going to be a y. And you have your negative k2y minus x pulling to the left. And then you have plus the force F of t, right, pulling it to the right. Again, this arrow goes this way, that's why it's negative. This one goes that way, it's positive, and that's it. So now all we need to do is to make these equations nicer, right? And we can also, when we multiply everything, we can separate x's and y's and all of that stuff. So let's take a look what we get. We get m1 x double prime is equal to negative k1x plus k2y minus k2x. And the second equation, because you should always have them paired, is minus k2y plus k2x plus f of t. Now we are going to put these x's on a pile and y's on a pile. So we have mx double prime is equal to, now coefficients of x, we have negative k1 and negative k2 times x plus K2Y, and the other one is M2Y double prime is equal to K2X minus K2Y plus F of t. And now, as you can see, we do have something that resembles a system. If you guys go back like 4 or 5 courses, you were looking at the systems 3x plus 2y equals to 7 and I don't know, 10x minus y equals to negative 4, right? So I hope that you can draw the parallel between these two systems. Now your x and y are functions, but these are still systems. And this is what we say system of differential equations. Because what you have here, yes, it's a second derivative and all of that stuff. We're going to deal with the first order, blah, blah, blah. But the idea is that you can set up these systems very easily, and then when these k's are given to you, right, they all turn into numbers, and the mass turns into a number, and you're just going to have a system. Let's see if, just real quick, the homework, if they give us a situation. They give us a situation with 3 springs actually there. Well, that's okay. Is there anything? No. Well, that's okay. I mean, when you have a picture, right, they will give you the numbers and you just plug them in, and then you have the system. Again, we are not learning the way to solve this. We are learning the way to set up and what it means to have a system. So this would be the system of 2 differential equations. Functions x of t and y of t are unknown functions, right, which you will get when you solve the system. And again, solving this system is not something that we would be concerned with right now. We are just now setting up the system and understanding the situation. Another situation that they presented, and we'll do all 3. So the second one is the one with tanks, when you are mixing solutions. So this is the equivalent of 1 plus 1 equals 2 for chemical engineering. So, if you don't understand this problem and don't care to learn it, you will get absolutely nowhere in chemical engineering, because mixing solutions obviously is the primary concern of chemistry. So you have a tank, and you have another tank, and those tanks are connected with pipes through which the solutions are allowed to flow back and forth. You have the intake into the tank over here. You're putting the stuff inside, and then you have the exhaust on the other one, taking the stuff outside of the other tank. So this would be a tank 1, that would be a tank 2, and then we're going to have the solution. Now, I don't care what you are mixing, right? You can be mixing 2 gasoline solutions, like one would be more octanes than the other. For instance, when you go to the gas pump, right, you have regular, and then the plus or super or whatever it's called, and then the premium. Now, when the truck rolls in, right, they only carry premium and the regular, and then the one in the middle is mixed with the 2 of these. So to get that octane, right, on a different level for that medium price. So what you are going to have in this situation is some liquid coming in, and then you will have the liquid coming out. Now, see, the trick here is to understand that these could be it's the best, obviously, if those are the same value, because if you are having more coming in than it's flowing out, then these tanks are going to overfill. If you have less coming in than what is being taken out, right? If you're taking more out than what you're putting in, then the liquid inside the tanks is going to run out and the tanks are going to be empty after some time. So generally, the amount of stuff coming in, which is, in calculus, that volume per dV dt, right? The volume per time. So dV dt coming in should be the same as a dV dt coming out, and then you don't have to worry about that. Now, but what do we actually worry about? Well, we worry about the size of each tank, right? So the book has this as a 100-gallon tank, and this one is a 200-gallon tank, meaning they're containing, one contains 100 gallons of liquid, the other one contains 200 gallons of liquid. They're full. And as you can see, if you start putting in and taking out the same amount of liquid, then they both remain forever full. Now, the trick is that you are going to have the flow between the tanks, and the first tank is going to have, they're using the salt and the water to mix. Now you can literally mix. You can literally mix whatever you want. So you can mix literally anything. I said the gasoline, but it doesn't really matter. You're mixing whatever you want to mix. And the x of t, right, would be the amount of pounds of salt in the first. So x of t in pounds, and then y of t in pounds, which is the amount of pounds of, let's say in this case, salt you have in each tank. Now, the concentration of the salt is going to be x divided by 100 and y divided by 200. So that's the concentration. Because it is the amount of pounds of salt you have per unit of volume, right? The concentration of people per room is the number of people in a room, and then you can put the concentration of people per square feet or per square mile, like density of a city, right? Of how many people per square mile of area. Doesn't have to be city, could be any plot of land. So you can figure out the density, and it's very simple, right? It's how many people you have living in, let's say, 1 square mile of area. Well, concentration of salt in a liquid would be how many pounds of salt you have in how many gallons of water. So concentrations would be given by x over 100 and y over 200, because a 200-gallon tank, right? And y amount of salt. Now, this problem is obviously very important to figure out for chemical engineers, because concentrations are what you are worrying about, especially when you're making solutions, right, for sale and or use in further manufacturing processes. Now, what we are interested in, because now these two tanks are connected, putting the 30 gallons per minute water one way and 10 gallons per minute of water the other way, you can see that you can the water is obviously mixing here, right? It's mixing that salt, and these are two different concentrations, right? So it all gets mixed together, and you cannot separate these two processes at all, because they're connected systems, which is why we will get what we call coupled equations, because x and a y will show in both of these. Now, what are we setting up? Well, we are setting up the change in amount of pounds, amount of salt in each of the tanks. So the change of amount of salt is given in pounds, right? X would be X prime. So you are measuring on the change of salt, of amount of salt you have, the change of salt in time, in this case, per minute, right? And that's that dt. So dx dt is change of salt in time, and that's going to be equal to, so now tank is our, tank 1, right, is our host tank for x prime, because that's where the x of t lives, so x prime is going to be measured there. And we see that we have the outflow of 30 gallons per minute, right? So that is going out of the tank, so minus 30 gallons per minute, right? And that's going to be, well, let's not use the units here, we can talk about it later, times the x over 100, which is the concentration of salt in that tank. And it's gaining, so you can think of this as a loss, right? That's a loss. It's losing because it's giving away those 30 gallons outside of the tank. Now, the gain is 10 gallons per minute of the concentration Y over 200 from the other tank, and that will be a gain, which is why it's plus. So the change in salt, the amount of salt that you have in the left tank, tank 1, is going to be losing 30, right? That's the change, because we are giving away 30 gallons at the concentration of x over 100, and we are gaining 10 gallons per minute of concentration y over 200. And now you write the same way the equation for tank 2 from the perspective of change in y. Now that one is going to be gaining 30 of x over 100, right? Because that's coming in, and it's going to be losing 10 y over 200 because that's flowing out of that tank. And now, since we are not adding or subtracting any of those, right, we have, I forgot one more thing. When you are putting in a clean water over here, and over here salty water, well, solution is coming out. So technically the system is getting diluted all the time because the salt keeps draining with the exhaust. I forgot about that. You have the clean water coming in. That's not going to add to the salt we already have. But we do have on the outflow, on the exhaust here, we have the salt leaving the system, the one that it's mixed in with the water. So we also have a loss, right? Another loss. And this one over here is 20 gallons per minute. And that's going to be 20 of the concentration Y over 200 due to exhaust. So obviously over time, since we have, when we started this system, you had X amount of salt in the first tank, Y amount of salt in the second tank, you flood everything with the water and you start mixing. You turn the water in, clean water coming in, and then the salty water coming out of the tank 2. you can see that since you are always adding clean water and the solution is flowing out, everything is getting more and more and more diluted. So now, wait, this negative 20 was supposed to be on the bottom equation, guys. Tank 2 is losing this, not the tank 1. There we go. Tank 2 is losing exhaust. Tank 2 has the exhaust. So it's a very straightforward situation to set up. You take a look at the tank and you count everything that it's flowing in as the positives, everything that it's flowing out as the negatives, and you are multiplying those rates by the concentration of the salt, which is whatever amount of pounds of salt we have. That's why they're X and a Y. Divided by the size of the tank, which is how many gallons of water you have in that tank, and that gives you the concentration. So now what you can do is just clean up these equations real quick, and you have your system. So X prime is going to be equal to negative 3x over 10 plus y over 20, and we're going to multiply that by 20 to kill the fractions. And then y prime is equal to 3x over 10 minus y over 20 minus y over 10, and that one is going to be also multiplied by 20, and we can combine those two terms. So once you multiply everything by 20, you get your 20x prime equals to negative 6x plus y. And on the second one, you have your 20y prime equal to 6x, and now this is going to be minus 3y altogether, right? Because you will have minus y minus 2y is minus 3y. Yeah. All right, cool. So there they are. This is your system. And again, x is going to be the amount of pounds of salt as a function of time. And the y is also going to be that, and that's going to be time measured in minutes because all of our rates were in minutes. So whenever you start this mixing procedure, you will be plugging in values in minutes to calculate the concentrations and literally everything you care about in this system. Again, we're not solving this, we are setting it up. Now, in terms of solving these systems, right, maybe you already see that, adding these equations will eliminate x. You will only have negative 2y. You will have this side, and there's some derivatives can be taken and stuff can be plugged in. But again, the methods of solving these are the rest of the chapter 4, chapter 5, and beyond. So even chapter 7 is going to have some insanely cool things that you can do. Electrical circuits, same ideas, except now instead of having one RLC loop like last time, you are going to have 2 or more. And each loop now is going to introduce more of these equations that you have to consider. Now, electrical systems tend to be a little bit more involved because you are going to have different currents, and you have to learn Kirchhoff laws and all of these things to set these things up. So I am tempted to skip over electrical engineering ones right now and talk about them when it's time to talk about them, just because you have to learn additional physics. Mechanical problem and the mixing problem, those were straightforward. We did not have to learn anything extra from the basic knowledge of the world that we already have. Now, learning Kirchhoff laws and following the nodes and setting up the equations. So I'm just going to hold off on electrical stuff, even though it's not too complicated. but still we need to focus on the task here, and the task is to introduce systems. We will have applications later where we actually solve these problems and get some solutions. So now let's take a look at some at the representation of these systems, and that would simply be a couple of differential equations. So some f of, and then you have your independent variable t, and then you have x, y, x prime, and y prime equal to 0, and g of t, x, y, x prime, y prime equal to 0. So here are the two equations, and clearly they are first order because the only derivative that you see inside is the first derivative. Now our mechanical problem did not qualify for this because of the x double prime, right? But our mixing problem for tanks, right, does fit into this category. We do not have any of the terms that only contain t in our system, but there could be some forcing function added, like e to the t or something like that, that would make things more complicated along the way. And that would be then this case, the function of t of some kind, like e to the t, sine t, whatever you come up with. So the first order system will contain, and generally it contains, right, all four of these, and then sometimes they contain t as well. Now, if you look at the mechanical system that we had, even though it is the double prime, it had that component, right, of function of t in there. Now, again, it doesn't work with it's not a first order, it's a second derivative, but still, it was a really cool problem for us to see how to put these equations together. So now, when we have the system of equations, we are looking for the solution of the form, right, x of t and y of t. So those will be two separate functions which, working together would both satisfy the system when you plug them in. So your old systems from pre-calculus and algebra, right, two equations and two unknowns, they had a point x comma y as a solution, and then you can plug in your x and you plug in your y and you can check the answer, right, making sure that that solution is valid. Now, right, in differential equations, you have systems of equations and the solutions are functions, and you can do the same thing, right? Once you solve the system and get your x and the y as functions, you can plug in your function x, you plug in your function y, you plug in the derivative of function x, and make sure that left side equals the right side. I mean, that's going to be the same idea as what you had before. Now, there are other methods in solving this. So when you have a second derivative lurking around, you need to have three equations, right? And then you would have you would be able to solve. I mean, we'll see how these things develop over time. So for electrical problem that I didn't, right, present to you, we'll have the Kirchhoff laws, and then you would have two loops plus a node that would give you three equations that you would work out to come up with a solution. So you would have two double derivatives and one equation that has voltages, but we'll deal with that when we get there. Now, what we are focusing on in this section is understanding that we have systems of differential equations, and we have seen that. And then those systems don't have to be just with the first derivative. They could have second derivative, third derivative, 10th derivative, and so on. And we can actually break those higher systems into the systems of the first derivative only. And that is a very powerful and very cool technique to have something like that given to us, because we know how to solve some of those equations. So what I want to show now is the way to break, let's say, a differential equation, which is a third order or a fourth order or whatever order, into a first order system. Again, we are not solving it. We are learning about systems, and we are learning how to write and develop these systems. The rest of the chapter is devoted to solving systems. So here I have a second order differential equation. Let's say x double prime minus 4x prime plus 5y equals to 0. So this is a very simple equation. You know how to solve from 3.1, right? It's something like this was part of the exam even. Not y, x, they're all x's. There we go. So you have this written in the, right, and you can write the characteristic equation with those r's, and then you can factor, and you can come up with those r's, and then write the solution with ease. And if it's complex, right, you write the sine and cosine, and so on. So you know how to solve this. Now I want to present you with a method to turn this particular equation into the system of equations. And then you can use the methods of the systems to solve and obtain the same solution at the end. Now, obviously, right, you don't use the sledgehammer to solve something simple, but you can, right? You can, so why not? Now, the method works this way. If you have only one variable function, x, you need to create two variables, x1 and x2, which will replace eventually this x and create system that will contain x1 and x2. Now, how's that achieved? So you start with writing that your x1, now this is what we are learning. So you're writing that your x1 is x. Guys, these are all functions. This is me writing x1 of t equaling x of t. And I'm just dropping this notation for t's. These are not variables, these are functions. So x1 equals x and x2 equals x prime. So this is where you start. Now, we know from the first equation that x prime is equal to x1 prime. And you can plug that in. So technically, your x2 is equal to x1 prime. And now, this is technically problem solved, right? Because all I need to do now is to plug these things inside the original differential equation and come up with the system. Remember, I am not going to have any x's anywhere in the system. Everything has to be x1 and x2 because we are converting the x system into the coupled system that will only have x1s and x2s. So now, armed with this equation over here, I have my first equation, x1 prime is equal to x2. And the question is now, what is x2 prime equal to? Well, x2 prime is equal to x double prime. So that's our second equation. But remember, we are not allowed to have x's, right? So looking at the top equation here, let's go maybe orange. From the top equation, x double prime is equal to 4x prime minus 5x. When you simply do that arithmetic. And now this x double prime is 4, x prime is x2, minus 5, and x is x1. So now, when you replace that in here, you get your x2 prime is equal to minus 5x1 plus 4x2. And there it is, system of equations. I understand it's a little bit convoluted to get there, and there's a lot of substitutions and back and forth, but luckily YouTube has a replay, right? And half a speed, so I can, right, really speak slowly. And you can go through the procedure and try to make sense out of it, and then you make your own problems, because you can literally put whatever you want. It's important to follow the flow of what's what. Let's do the third order. It literally doesn't matter what you put as your equation. Let's do y's. Y triple prime minus 2y double prime plus 6y prime minus 10y equals to 0. So now we have to come up with 3 equations, right? We're going to come up with 3 equations because we had the third degree. It should kind of make sense that the third degree differential equation will break down into 3 first degree equations. The 5th degree differential equation will break down into 5 first degree equations. Because the order has to be the same, right? Whether you have 5 first degree equations or 1 5th degree equations, it should be the same. They're going to look different, they're going to be solved differently, but they must have the same solution in the end. So now, how do we break this one up? Well, we do the same thing as we did above. We're going to assign y1 variable to be y, y2 variable to be y prime, and y3 variable to be y double prime. You always start with the setup with a number of variables equaling the order, and the highest order will not be represented in this first setup. So you can say let, right? Let these variables, right? It's like assigning variables in your computer code. So now that we assigned all of these variables, there are things that I can use and start plugging things in where they belong. So the first order of business is to differentiate here and plug in there to come up with y2 is equal to y1 prime. That's actually already your first equation, right? Your y1 prime, your system is y1 prime equals blah, y2 prime equals blah, and y3 prime equals blah. That's your goal, right? Because we learned that the first order system is the first derivative for a variable equals whatever it has on the right hand side. Here it is. First derivative of the first variable equals blah, and the first derivative of the second variable equals blah, right on the other side. Blah meaning whatever it gets to go there. So that's our goal, right? And I already achieved that goal here because I have the first derivative equals to y2, so I'm actually done with the first one already. But let's not get too excited. We have to keep pushing. Now, what are we going to do for the next one, right? Because now I need to differentiate. Maybe I should, let me do the blue box around this one. Now, the next step is purple. So I'm going to go into this equation, and I'm going to say that y2 prime is equal to y double prime. But I know from here that y double prime is y3. So now this one and this one together are going to give me that y2 prime is equal to y3. I hope you can see that. So we take this equation, we differentiate that, come up with y2 prime is y double prime, and now you already have this left side of blah, there it is, but it's equal to y double prime. You're not allowed to use y's, you have to use one of the three new functions, y1, y2, y3. Luckily, this equation tells you exactly what y double prime is. So you got your second equation, and that second equation is this. The only thing that is left, and for that one we're gonna go green, I guess, is to differentiate with time and get that y3 prime is y triple prime. And you can go back to the original differential equation to come up what y triple prime is when you ship all of this to the other side. So now the part of this green thing is the notion that y triple prime is equal to positive 2y double prime minus 6y prime, and I think minus 10y, plus 10y. Plus 10y, because they all go to the other side of the equal sign and they all change their signs. So now these two mushed together will give me y3 prime equals to 2y double prime minus 6y prime plus 10y. But we are not allowed to use y's, just plug in y1, y2, y3 because we have them defined. You see that y is y1, y prime is y2, so you just replace them in. So y3 is going to be 2y3 minus 6y2 plus 10y1. And that would be your third equation. So now we have all three equations blue. So here is your first order system. only first derivatives are present. y1 prime was y2. y2 prime was y3. And y3 prime is 2y3 minus 6y2 plus 10y1. Ta-da! No y's. They're all y1, y2, y3, new functions that we used. You eliminated the second and the third derivative from the problem, and now you're dealing with a system of equations with three unknown functions, and they're going to come up, right? You're going to come up with y1, y2, and y3 eventually. And guess what? Once you find your y1, that's your y. That's the answer, right? Because the original problem is only looking for y, but your y is equal to y1. So as soon as you find y1 from your system, you have your y, which is the solution to the original problem. So next time when someone says, what do you know? Yeah, show them this. See if they can make sense out of any of that stuff. Obviously, learn it first. Don't go there and say, look at this, and then you just get stuck and you have no clue what's going on. So be careful about that. Should we do another one of these? Anyone? Is anyone still present over here? All 9 of you.
I'm thinking about what that shape was. What is it?
You're still hung up on the before the class?
Well, yes and no.
The thing I had?
Yeah.
It's the first order symbol from Star Wars.
Oh, wow.
Yeah, that's why I'm saying it's really concerning that literally no one got it.
I thought I was missing out on some heavy math.
You were. The Star Wars is the philosophy of life, which is, what I said like 1,000 times. Someone says, I'm in STEM, and I say, how about Star Wars? And it's like, I've never seen it. I think
I do recognize the symbol now that you said what it is.
Good. So you're saved. I'm not sure about the rest of the people. All right, troops. You know what? Let's take a look at one more of these to kind of just do the transformation from a single differential equation into the system. So here is problem number 6 from homework. So the fourth derivative, need 4 equations, plus 6x double prime minus 3x prime plus x, and this one is equal to cosine 3t, which you will just drag later through. That cosine 3t will just appear right here in the last equation. So you don't have to worry about the cosine 3t at all. It is more like, let's define all of the 4 variables, right, and new functions, and then go from there. So you have your x1 equal x, x2 equal x prime, x3 equal x double prime, x4 equal x triple prime, and remember the highest order is not represented in this let line. Now I'm going to give you about 5-6 minutes to try and wrestle your way through this, and then I'm going to work this out. I have to swap up the cooling for the tablet, and get the bottle of water. So I'll be back quickly, but you try to resolve this as much as you can. I'll be right back.
Is that his phone?
Okay, let's take a look at the problem. What do we have? We have the derivative on the first one equaling x prime, and from the second one x prime is x2, so we are getting that x1 prime is equal to x2, which is our first equation. Let's do the blue like we did in a previous problem. So we have one of our equations right away because we were able to do that. Now we're going to go, let's go orange, differentiate x2 prime. That will give us the x double prime. And from this equation, we know what x double prime is. So x2 prime is x3. And that gives us second equation out of 4. Purple. We are going to now differentiate this one and get x3 prime equal x triple prime. Now we know what x triple prime is from the next equation, and that gives us that x3 prime is equal to x4. Very systematic. The last one, let's go green, is when we differentiate this one for x4 prime, and that gives us x fourth derivative. Now we can go back to the original problem and solve for that fourth derivative as negative 6x double prime minus 3x prime minus x plus cosine 3t. That was already on the right and it was positive, so that one doesn't change. And that gives us our x prime to the x4 prime, which is negative 6. Now, what was x double prime? It was x3 minus 3 x2 minus x1 plus cosine 3t. And that's our fourth equation. Now all we need to do is to write these equations in order, and we're done. So x1 prime is x2. You can leave some space for x1 from other problems. x2 prime is x3. x3 prime is x4. And x4 prime is negative x1 minus 3x2 minus 6x3 plus cosine 3t. There is the system. So we reduced our problem from what do you call it? Reduced our problem from the fourth degree single equation into a system. Does it have benefits? Yeah, it does. And the reason why you have benefits from here is polynomials. Remember that this would be your characteristic equation r to the 4 plus 6r squared, right? So it will be a polynomial in R. Polynomials are really nasty creatures. They are absolute nightmare to factor. We have some very easy factoring techniques when you have special cases of polynomials around. And then for quadratic polynomial, right, which is trinomial, you can use quadratic formula. For third degree already, the formulas are terrible. You can look them up. Fourth degree, I don't even want to talk about because it's borderline insane. to try and solve those using formula. And then there is a proof in mathematics that procedures and formulas for 5th degree and up cannot even be made. So polynomials are really, really nasty for this, and that's why we have all of those approximation methods and all of that good stuff, which helps us not worry about factoring polynomials, but just use the numerical method in computer and bypass and factor it using computer. Now, we will see a different type of systems and ways to solve these problems. So it does have benefit, even though it looks like that you are going from the easier problem into a harder problem. The method of solving these problems tend to be easier than factoring polynomials, and you will understand that when you get there. Another thing that you might have picked up on is the pattern that it goes 1, 2, 2, 3, 3, 4, and yes, it's actually a pattern. We always had that in the previous, see, 1, 2, 2, 3, and then the last equation flipped. Here is the first example, see, 1, 2, and then the second one flipped. So now we have examples for the second, third, and the fourth order ODE converted into a system. You are welcome to go back with the video as many times as you need to come up with all of these systems. Now, there's only one thing left for us to do, and that is to solve very basic systems. And those systems are the complete joke in comparison to the stuff that we actually have seen. So let's take a look at one of those. We can go with, let's say, x prime equals to negative y, and y prime equals to, this is terrible numbers, 1.01x minus 0.2y with initial conditions x of 0 equals 0 and y of 0 equal 1. So solution for this system. Well, I hope that you can immediately pick up the fact that you can take the first equation, write it as y equals negative x prime, and then differentiate that system to come up with y prime equals negative x double prime. And at that point, all you need to do is to plug in, and you're done. That's how simple this particular system is. So you use one of the equations to solve, and then, right, for the prime, and then you just go and plug it into the other one, and you create technically the backwards procedure of what we had before. Now you create the second order system, because now the second equation here using this is negative x double prime is equal to 1.01x minus 0.2y, and move x double prime to the other side. You have x double prime plus 1.01x minus 0.2y equal to 0. And this is your now system, which you can use. Oh, wait, hold on. We're not done. I also have the y. So that's negative x prime, because everything has to be this. So now what you have is x double prime plus 0.2x prime plus 1.01x equals to 0. There we go. So now, as you can see, this is your standard 3.1 problem, where you just factor the polynomial using the characteristic equation r squared plus 0.2 r plus 1.01 equal to 0. So that characteristic equation breaks into using the complex roots. So you will have r to be 0.1 plus minus I, so that good old a is 0.1 and b is 1. So your solution here, x, because this was the x equation, x is equal to, x of t is equal to C1, no, lies, e to the 0.1 t times C1 cosine, b is 1, so just t, plus C2 sine t. So that was the complex solution from 3.3, I believe. It was there on the test, right? So when you have a complex solutions, you have your trig answer. And that is your x. Now you're supposed to find y using any equations that connect x and a y, just like in the other systems, right? You find either x or y, and then you go in and calculate the other number. Now you found the function solution for x, find the equation that connect x and y, and go compute y. Now that might involve integration, might involve further differentiation, whatever. Let's see what we got. So where is the connection between y and x? And here it is. So y is equal to negative x prime. Y is equal to negative x prime. Well, find x prime. Yes, it's a product rule. I know. It's not going to hurt too much. Y of t is equal to copy the first times derivative of the second plus copy the second derivative of the first. And now we have those conditions, x of 0 is 0 and y of 0 is 1, to solve this. So we're going to have x of 0 is 0 and y of 0 is 1. That was given to us. So x of 0 is 0. E to the 0 is 1. C1 times cosine of 0 is 1. Plus C2 times sine of 0 is 0. So from the first one, we calculate that. Yes.
Did you, when you took x prime, did you distribute the negative all the way through? Because y is equal to negative x prime?
I did not. Well, thank you. We can fix that either by changing the negatives in front or changing negatives inside. Let's put the negative in front. Very good, very good. I was testing everyone, and you clearly passed the test. You're paying attention. You're testing if anyone is paying attention. Yeah. All right, thank you. So
That's not the only test I passed.
Oh man, YouTube is not receiving enough video to maintain smooth streaming. Okay. Yeah, the tablet is getting a little bit overheated over here. Well, all we need to do now is to solve the second part. We got C1 is 0. So for our second calculation, C1 0 kills C1 terms. When I plug in 0, the sign terms will die as well. So all I need to worry about technically is that 1 is equal to -1 times C1 is 0. So that's going to be C2 times 1. So C2 is -1. And C2 is -1. Okay. Both of these terms here are zeros. First one is 0 because C1 is 0, and the second one is 0 because sine of 0 is 0. So both of them are gone. So this part does not contribute at all to that calculation. And now that I have this, I can write my solutions. X of t is equal to, remembering that C1 is 0, we just have e to the 0.1 t times sine t. Yes. And C2 is negative, so there is a minus in front. Good. And then y of t is going to be negative. C2 is negative, so positive. E to the 0.1 t, and which one survives? Cosine? Cosine t. And in the second one, this one dies. That's a negative. That makes it a positive. So plus 0.1 e to the 0.1 t, and the sine is the one that survives here because sine is C2, and that negative changed that to positive, and yeah, they're all good. There they are. That's the solution of the system. Mind that this was the easiest possible problem you can get. Well, not the easiest possible, because we had to shovel trigs with the complex roots. The easiest possible problem you can get is when they factor over real numbers, and then you just have like e to the 3t and stuff like that. Easy to differentiate and do everything with it. Repetition will have the product rule in a derivative, and obviously trig over here has the product rule in a derivative. So this would be what, the second or the third easiest possible problem you can get. Obviously there are systems with second derivative in it, and coupled 3 equations, and that is the rest of the chapter for that. Ta-da! That's it. It's like pulling a rabbit out of a hat. So when you have a simple system, you solve for the variable, differentiate, and then plug into the other equation. That's the solving it systems by substitution. Now, the next section, 4.2, is called method of elimination, and we're gonna go into that one and next class and deal with this. So that's it for this particular lecture. Hopefully you will go and review these problems a couple of times and learn how to break single equations into systems, or how to put systems into a single equation and then solve it using the method, which is the opposite situation. And also another thing is to be able to set up systems observing the reality around us, right? So I know we didn't do the circuits, but we will do the circuits when we do the application and we actually start calculating things. Bye.